In this problem, we are given the opportunity to calculate the modulus of toughness. We are given the elastic modulus of the material, the yield strength of the material, and the strain at fracture. So to get started, let's go ahead and plot a stress strain curve. And we have sigma, the stress on the y-axis, epsilon, the strain on the x-axis, and we have a linear elastic regime, which we can give by an elastic modulus, E, and then the material becomes perfectly plastic, as specified with the material model that we're using. This perfectly plastic model goes up to the yield strength and then it stays flat. So as we have more strain, the stress does not go up in the material. It breaks at a fracture strain or at some strain that's given by this length, and then in the problem it's given as 0.24%. We also probably want to figure out what the strain at the yield might be. So we have an epsilon y, or the yield strain here. And that, as we've seen in a prior problem, can be thought of or calculated exactly by doing the yield strength divided by the elastic modulus. The modulus of toughness is often given by U sub t and represents the area under the entire curve. And for this quote curve, we have an elastic region and we have a plastic region. So first, for the elastic region, we have what we also call a modulus of resilience, and that's just the area under this triangle here on the left. And we can see that that area would be half of the height times its width. That width is the yield strain, and we can think of that as, again, the yield strength divided by the elastic modulus. This comes from Hooke's law. So for the elastic region, we can write out that the area under that portion, or the modulus of resilience, will be 1/2 times the yield stress squared over the elastic modulus. The plastic region is this rectangular section where the yield strength does not, or the stress does not change and is constant as the yield strength. And here we can just think of coming up with the area of a rectangle. So this rectangle has some width, epsilon f minus epsilon y, the fracture strain minus the yield strain, and the height is going to be the yield strength, like we see here. And once again, we can calculate out what the yield strain is by doing the yield stress divided by the yield stress divided by the elastic modulus. So in the end, we add these two components together, and we have that the ultimate, or not the ultimate, the modulus of toughness, it's a U, but it's not the ultimate tensile strain, is 1/2 times the yield strength squared over E plus the yield strength times quantity epsilon f minus the yield strength over E. Well, let's go ahead and use a couple techniques here to perform this calculation. Probably first, simplest, is to use Google, although we're starting to see that there are a lot of terms here and we have to do some squaring and we have to be careful, but nonetheless we can do that. So the yield strength in this problem was given as 147 megapascals. So we do 147 in parentheses megapascals squared divided by the elastic modulus, which is given as 98, I'll put that in parentheses just in case, gigapascals. And we're going to do that plus the yield strength, which again is 147 megapascals. I'll put that in parentheses, though, just that. And then times, we have an epsilon f, which is 0.24%, like that. And we have minus the yield strength, 140, again, I put it in parentheses just in case, 147 megapascals divided by the elastic modulus of 98 gigapascals. And then we put another parentheses to close that one off right there. And we go ahead and we hit enter. And it says it's 243 pascals, or 243 1,000 pascals. And if we look here, we wanted this final result in kilopascals, all right? So we would divide by 1,000, and you can do that in your brain, or we can say, let's put this whole thing in kPa and see what it says. Yep, it did it, so 243 kilopascals. So that's one way to get a numerical result. The other is to go ahead, oh look, it's Jeff Hansen. All right, the other way we can go about doing this is to use Colab. And maybe this is starting to be a case where using Colab is good because we can assign numbers to these parameters, and if something changes in the problem, we can just change the variable values. So we're going to do import numpy as np, control enter. We're going to go ahead and start defining things. So let's say sy, it was the 147, yes, 147 megapascals, but I'm going to delete that and say just e to the 6 or e10 or times 10 to the 6, and we're going to say that's got units of pascals now. We have an elastic modulus, which was 98 gigapascals, right? So we have 98, and we'll do E9 from the get-go. And we have a yield or a fracture strain of 0.24%. So that's going to be epsilon f, and we'll say that's 0.24, and I'll do e minus 2, okay, and that's going to just be unitless. All right, and let's go ahead and say, okay, ut is 1/2 times, we've got our sy, asterisk asterisk is for squared, divided by e plus the sy times quantity epsilon f minus sy divided by e, just like that. I think that's right. Does that look right? 1/2, da, 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 da. All right, well, if we get an error, we get an error, we'll fix it. And then we can print this ut, and we can do an mp.round. And remember, they wanted it in kilopascals, so we'll do the ut. We can do, I don't know, 4 significant figures. Oh, no, that's decimal places. So we only probably need to do 1. But I'm going to do ut, and I'm going to divide by 1,000 here. That will give us the units of kilopascals. Okay, so kilopascals, just like that. Okay, we run this, and what do we see? We get 243 kilopascals. So I hope this problem makes sense and you found this example helpful. Thank you.